Okay, hopefully you've watched the Euclid division algorithm video, and what we're going to do now is finish this last step in finding the inverse of our encryption key matrix mod 29. And where we left off is we had reduced that original matrix to this main diagonal. We have 27, 45, and 135. Well, we need to figure out what the inverses of these numbers are mod 29 as opposed to the inverses of these numbers in the real number system. Normally we would just multiply each row by 127th, 145th, and 135th respectively, but we can't do that in this case. So the first step here is to reduce each of these three numbers into the mod 29 number system. And so 27 is already good, but 45 is the same as 16 mod 29. So let's, as an example, we're going to take this 45, which is the same as 16, and we're going to find the inverse of 16 mod 29, and that's what we'll multiply this row by in order to do the final step for our inverse of our key matrix. So let's take a look at that. Okay, calculating the inverse mod 29 of 16, we use Euclid's division algorithm to figure out the greatest common divisor of 29 and 16, which we already know is 1 because 29 is prime. So we have 29 equals 16 times 1 plus 13. 16 is equal to 13 times 1 plus 3. And we continue with Euclid's division algorithm until we get down to 1. 13 is 3 times 4 plus 1. And now we know that 1 is the greatest common divisor of 16 and 29. The key trick here to using Euclid's division algorithm to figure out the inverse of 16 mod 29 is to reverse Euclid's division algorithm. What we know is that the inverse of 16 is the number we multiply 16 by to get one more than a multiple of 29. We want 16 times x to be 1 mod 29. That is to say, we want 16 times x to have a remainder of 1 when we divide it by 29. And so what we're going to do is solve for 1 in terms of 29 and 16. And so we start with this last line, and I'll bring it up over here. So 1 is equal to 13 minus 3 times 4. Okay? But I know that I can express 3 in terms of 16 and 13. So I'm going to express this 3, which is this 3, in terms of 16 and 13. And so I'm going to say that 1 equals 13 minus, but instead of 3, I know that 3 is 16 minus 13. So I'm solving for 3 in the next step up. So this is 16 minus 13 times 4. This 4 is the multiple of 3. Okay? And we simplify that a little bit. We say that 1 is, what do we got here? 13 minus negative 413, so that's 13 times 5 and 16 times negative 4. Okay, so 16 times negative 4 and 13 times 5. Okay, and you can check this along the way. 16 times 4 is negative 64 here. 13 times 5 is 65. 65 plus negative 64 is 1. So we're good. And we keep going, right? I want to get rid of the 13. I solve for 13 in the next step up in Euclidean division algorithm. And I know that 13, I still have 16 times negative 4 plus, and now 13 is 29 minus 16. 29 minus 16 times 5. Okay? And now we're almost there. We just combine, I guess we could call them like terms here. We combine multiples of 16. We've got 16 times negative 4 and another negative 16 times 5. So that's a total of 16 times negative 9 plus 29 times 5. And let's double check one last time. 16 times negative 9, what's that? 90 plus 54 is negative 144. And 29 times 5 is 145. So indeed, those together are 1. And so you look at this and say, okay, well, negative 9 isn't in the mod 29 number system. So even though this combination gives me 1, I need a multiple of 16 that's in the mod 29 number system. And so all I have to do here is figure out what is negative 9 in the mod 29 number system. And that's a pretty easy thing to do. We just add 29 to this, and we get that 20 is the inverse of 16 mod 29. Okay, and you can check that, right? 20 times 16 is 320, and I honestly don't know. 320 divided by 29 is 11 with a remainder of 1. 11 times 29 is 319, and so we've done it. Okay. You want to do those for the remaining two values in your diagonal, and then you would just multiply each row by that value, and you are set. Okay. Hope that helps. Just as an explanation of the instructions there, I realized maybe some of it didn't make sense. In part 2b, where it says each row factor out the denominator, what I meant by that was if we had continued using Gauss-Jordan and we multiplied this row by 1/27th and this row by 1/45th and this row by 1/135th, we'd have our normal real number matrix inverse. So I meant factor out the denominators. This would have been 2 over 27, negative 4 over 27, 3 over 27. I mean, factor out the 1 over 27 and realize that instead of 1 over 27, we need the inverse of 27 in the mod 29 number system. So if that's confusing, part B, that's all I mean is instead of multiplying by 1/27th, realize we have to find the inverse of 27. And hopefully that makes sense. Now once we have the inverse, we can go back and multiply that times your ciphertext matrix, and you should get the matrix that tells you the original message. Good luck.